G'day, my name is Ben Hardless. Welcome back to the 2600 playlist. Today I just wanted to talk about roots of complex numbers. And what do I mean by that? I mean, if you are familiar with something like this, right? You could say that if x is equal to the square root of 16, then what are the solutions for this, right? It's kind of like saying what squared is equal to 16, yeah? So the answer to this, hopefully you can see, is going to be 4 or -4. And, you know, this is interesting. This is a square root. This is the same thing as writing 16 to the power of 1/2. You know, it's a fractional exponent, finding the root of 16. And, you know, it's interesting that there's two possible solutions here. And you do find that with these square roots. Similarly with cubic roots, you'll find that there's typically 3 solutions. If you're familiar with this idea, which I'm assuming you all are, then this idea of complex roots should not be too much of a stretch for you. So let's just dive into an example and get underway. We have a complex number which is z equals 2 plus 2 root 3j. So we want to take the square root of that, right? So z square root equals what? And I don't know why I put it in the middle. I should probably move it over to the side. So z to the power of 1/2 is equal to 2 plus 2 root 3j, all to the power of 1/2. And it can be useful to write this in terms of e. So we could say that, let's find the magnitude of z first, hey? So what's the magnitude of z? That's going to be equal to 2 squared plus 4 times 3 square rooted. And so that'll be equal to 4 plus 12, 16, root 16, interestingly enough, which is going to be equal to 4. So we're only finding the positive root because we're taking an absolute value. So anyway, it's 4. So before we can write it in terms of e, we need the argument of z. So the argument of z, which is just the angle, is going to be, well, before we do this, remember we should always check what quadrant we're in. So we're 2, 1, 2 in the real, and we'll call that the imaginary, and 2 root 3. So you know, somewhere up here. Anyway, we're in this quadrant here. So no worries. What that means is that because we're in that quadrant there, the first quadrant, and you know, I haven't drawn this to scale or anything, but we're going to get some, you know, you can think of it as a vector z, and we're going to have an angle here, which is going to be a positive angle, and we can find it using inverse tan, where this is opposite and this is adjacent. So that's all cool. I'm just checking because it's not always the case you can use inverse tan like that, because for example, if you were over here, you'd be finding this angle with inverse tan, and that's not the angle you want, right? So I won't dive into that, but argument of z is going to be arctan opposite over adjacent, so that'll be the imaginary component over the real component, which is going to be equal to arctan root 3, right? Because the 2's will cancel out, obviously. So that works out to be pi on 3. So now we've got the argument of z. So now finally we can rewrite this square root of z is equal to the magnitude, which is 4 e to the j pi on 3. Now we are going to raise that to the half power, because we remember we're taking the square root of z, and this thing inside the parentheses is z. We're taking the square root of it. So we've got square root of z is equal to 4e to the j pi on 3 square root. And just like when we did the 16 example, the root 16 example at the beginning of all this, what we need to remember is that we're going to have more than one possible answer, right? So this is going to work out to be 4e the j pi on 3, and this is going to be square rooted because, you know, we're gonna do the square root to everything that's in the brackets here, and this is going to be multiplied by a half, so that's going to be pi on 6 plus 2 pi k on n, and in this case n is equal to 2 because the denominator of the fractional exponent is the n in this case. And if you don't know what I'm talking about, have a read of your book because it is right there. So this will be equal to 2ej pi on 6 plus pi k, where k is equal to 0 and 1. So let's see what happens when we do this, because there's going to be 2, so we'll just call one of them Z1, we'll call the other one Z2 just for convenience. So if k is equal to 0, then we will get 2e to j pi on 6. Now what does that actually look like? So I've drawn a little diagram here. We've got the real and the imaginary axes, and so we've got the pi on 6 is the angle, and we've got the magnitude of 2 being the length of the, you know, the vector, if you like. And so what are the actual real and imaginary components going to be? Well, we can figure that out because remember, this z to the ej pi on 6 is going to be the same thing as cosine pi on 6 plus j sine pi on 6. So it turns out that cosine pi on 6 times 2 is root 3, and sine pi on 6 times 2 is 1. So that means that this, and I'll just change color so you can see it, it means that from here to here, that is a length of root 3, and from here to here is going to be 1. So that's one of the roots. Now let's look at what Z2 is going to look like. So Z2, the second root for Z is going to be equal to when k is equal to 1. So remember, we found this out up here, and we're going to now say that k is equal to 1. So it's going to be 2e to the j pi on 6 plus pi. Righto, well that doesn't seem so bad. So what's pi on 6 plus pi? So this is interesting because really all that's going to happen is we've got the same magnitude, but we're going around pi radians. Pi radians is 180 degrees. So if you imagine from this guy, we're going around pi radians, right? So what we're going to end up with, and hopefully you see this, is we're going to end up with something that's magnitude 2 here, and we're going to end up with an angle which is this guy here. Double line him, beta 2. Okay, so that's interesting. What we're going to get is something out here, and hopefully you can see that this length here is going to be root 3, and that and that's, I'm talking that there, and then this length here, right, is going to be 1. So let's see if that is indeed the case. So we're going to get 2 cosine pi on 6 plus pi plus j sine pi on cx plus pi. So this comes out to be, you guessed it, negative root 3 minus 1. So that's pretty cool, because what you can see is that this is root 3 in the negative direction, right? So we say that's negative root 3, and we're going 1 down from the 0 point on the imaginary axis, so that really is a negative 1, isn't it? And these seem to be equally spaced, and if you had if you were taking the third root, so you were raising a complex number to the power of a third, you would end up with 3 points equally spaced on the Argand diagram. So I hope this has been helpful to you, and I'll see you in the next video. Bye.